Hey guys, welcome back to day 18. We're talking about the composition of compounds and we'll do some examples. So day 18 and day 19, they really go together. But day 18 first. Mass percent. So the first thing we're talking about is mass percent. And as you can see, it's an element's percentage of the compound's total mass. Mathematically, so the mass percent of X, whatever X is, right? So if we want to calculate the mass percent of X, is going to be equal to the mass of X in 1 mole of compound all over the mass of 1 mole of compound times 100%. The mass percent. So for an example, calculate the mass percent of sodium in sodium oxide. Well, we want the mass percent of sodium. So we look at the periodic table. Sodium weighs 22.99. And the units are going to cancel. So grams per mole. Sodium oxygen, 22.99 grams per mole. And then oxygen 16. Add those and multiply by 100%. And if we do that math, I would get 58.96. I got 4 sig figs, so 58.96% Na by mass. That looks beautiful. And everything mathematically we did right there. There is a problem. So in class, I would usually stop right now and say, this answer is wrong. Why is this answer wrong? Right? And the question is, what did we miss? Well, we did the cardinal sin. We did not write out the chemical formula. So step 1, we write the correct chemical formula. Step 1, or step 0, if you want to call it step 0. Sodium, Na plus. Oxide, O2 minus. So right away, we notice that it should be Na2O. So really, the mass percent of Na would be 2 times my 22.99. Oh, didn't change. 22.99 grams per mole divided by the 2 times the 29.99 grams per mole plus our 16.00 grams per mole times our 100%, and I actually get 74.19% Na by mass, which makes sense because it's mostly sodium. So the takeaway here, hopefully, because mass percent overall, probably not that difficult, not really a new concept for most of us. It's the percentage of anything. The new thing that we have to do is be patient and always make sure we have the right chemical formula. Vital. So this leads us now into the stoichiometry of compounds. Going back to formulas, right? Very important. So the composition of a compound is indicated by a formula. All right. What does this formula provide? It provides the relative numbers of atoms of each constituent element. It also provides the mole ratio. Which of course is the particle ratio. And that particle ratio is very important. So if we take an example, water, H2O, we know we have 2 atoms of H and 1 atom of O in 1 molecule, or 2 moles of H and 1 mole of O in 1 mole of water. Recall that mass divided by molar mass equals moles. Calculations usually involve converting a mass ratio into a mole ratio. Why? Because we measure things in mass. We can measure almost any substance in mass. Gases a lot of times in pressure, sometimes liquids in volume, solids in mass, sometimes liquids even in mass. We can measure mass very, very easily. And the thing is, most of our compounds, we don't have the mass ratio for the reactions. We can always go to moles, and then we use the mole ratio for reactions. So go back to cooking. When we do a reaction, spaghetti, for example, you know how much noodles, how much sauce, how much of everything you're going to put in there. And you count them, and you know the ratios, right? You don't actually have to weigh things, probably, right? You just know your ratios, and you go with your ratios, and you make your spaghetti or any other recipe you're going to follow. If you're an expert baker, measuring, and some of you guys might weigh. So using measuring cup, you might weigh your flour or weigh your sugar or weigh your whatever you're going to put in there versus just measuring the volume, because weighing is more accurate. When we do chemical reactions in a lab, we don't have the ratios and the recipes, all that written down. We have chemical reaction, which gives us the recipe with the mole ratio, and so we come up with chemical formulas. We use molar mass to get to that ratio. Now let's talk about the formulas. Right? There's 3 formulas we're going to talk about. So first, you do the example of benzene, which is C6H6. The molecular formula is C6H6. All right, and that's just the formula for the molecule. That gives us how many of each individual atom are present. Then there is the empirical formula. For benzene, it's CH. And this is the lowest ratio of atoms. Note, all ionic compounds are written as empirical formulas. They're all written as empirical formulas. And the reason they're doing that, because it's a ratio of cations to anions. Last but not least, there is the structural formula. And this shows how atoms are bonded. So what about the structural formula for benzene? It's going to look something like this. And we will learn how to do that. That's exciting. So now let's apply this mass percent to empirical and molecular formulas. Because, why would we do this? So in the lab, when we make stuff, it's a little bit different than making stuff at home. If I make cookies, I should know what they look like. If I make steaks, if I make a cake, if I make spaghetti, we know what those look like. Like, this is spaghetti. Sure it is. It's got frosting on it. You know, it's a cupcake. Don't tell me it's a spaghetti. Here, in chemistry, a lot of the compounds, you can't tell. I mean, you start with a white powder, you end with a white powder. You can't necessarily tell the difference between them, right? If I would give you, leucine, which is an amino acid you can buy pure, arginine, which is another amino acid you buy pure, ibuprofen, that's just white ibuprofen that you can ground up, aspirin, all these you could just ground them up. It'd be hard to tell the difference without the label. It's kind of like going to the pantry, and if you have canned goods, you have just your cans, and you know they're different cans, but they're just take all the labels off. So instead of it tells you it's canned green beans or canned sauce or canned corn or black beans, all labels are gone. So you don't know if you're opening up black beans or ravioli. Okay, that's like, how do you tell what you have? And so we can do techniques, right? Whether we're going to get to eventually combustion analysis, but we can use techniques to figure out the percent mass of the elements and figure out what they are, what the compound is. So let's start. Number one, you have an oxide of copper. Well, what are my two elements? Cu and oxygen. Cu and O. Now we know it's 88.82% copper. Well, what's the total percent going to add up to? Well, it can only equal 100%, correct? So how much is oxygen? I would take my 100% minus my 88.82, and that would be 11.18% oxygen. Right? The question is going to ask, what's the formula of the oxide? Well, it's ionic compound. How do I know it's ionic? Well, copper's a metal, oxygen's a nonmetal, ionic compound. And so we want to calculate the it's ionic. We want to calculate the empirical formula. So step 1, I have a percentage. It's a mass percentage. So I'm going to assume, right, 100 gram sample. So I'm going to assume I have 100 grams. So if I have 100 grams, I have 88.82 grams of copper and 11.18 grams of oxygen. Right? Do I have to have 100 grams? No, I can have 2.12 grams or 5.1 grams or 0.24 grams. It doesn't matter what the grams are. I have the percent, I have the ratio, right? A percent's a ratio, so I'm just going to assume I have 100 grams and make it easy. Step 2, I want to get to moles. So we're going to convert to moles. How? I'm going to divide by the molar mass, because that's the ratio of grams to mole, right? Molar mass is grams to mole. So for copper, the molar mass of copper is 63.55. For oxygen, it's 16.00. That gives me 1.398 moles of Cu and 0.697 moles of O. And that's technically my mole ratio, 1.4 to 0.7. And you might know what they are as whole numbers, but we want them whole numbers. So step 3, we're going to convert the mole ratio to whole numbers by dividing, let's make my divide sign, dividing by the smallest. So divide by the smallest, which of course is the number for oxygen, 0.697, 0.697. And if we do that, we get 2 for copper and 1 for oxygen. So my empirical formula would be Cu2O, and that is copper 1 oxide.